Hey there, have you ever actually stopped to wonder what's going on inside your computer, like right now? We're about to pull back the curtain on the fundamental magic trick of all modern technology, how our rich, complicated world gets translated into the super simple language of machines. It all boils down to a simple, almost ridiculously basic question. Deep down, a computer is just a massive collection of tiny switches that are either on or off. That's literally it. So how do we get from that simple reality to, well, this? To you watching this, hearing my voice, and seeing all these graphics pop up on your screen. And this is the heart of the problem, right? On one side, you've got us, humans, with our rich, nuanced data. Words, pictures, music, you name it. And on the other side, you have the machine, which only gets two things. On, which we'll call a 1, and off, which we'll call a 0. That is a huge gap we need to bridge. And the bridge across that huge gap, it's a process called data representation. Think of it as the ultimate elegant translator. It's the system that takes all of our complex stuff and converts it into that simple binary format that computers can actually understand and work with. So how does this whole translation even begin? Well, it starts with the absolute basics. We're talking about the fundamental alphabet of all digital information. Everything, and I mean absolutely everything in the digital world boils down to this one thing, the bit, a single binary digit. It is the smallest possible piece of data you can have. Just one switch that's either off or on, a 0 or a 1. Simple as that. But a single bit by itself doesn't tell you a whole lot. So what do? We group them up. A group of 4 bits is called a nibble. A group of 8 is a byte. And that one's super important. You should remember that. Think of it as the standard-sized chunk of data. And then you have something called a word, which is just the biggest chunk of bits a computer's processor can handle all at once. Now, you might see this number, 1024, and think, what on earth does that have to do with anything? Well, let me tell you. 1024 is one of the most important numbers in all of computing. Why? It's because computers don't think in powers of 10 like we do. They think in powers of 2. And 2 to the power of 10 is 1024. And that's why this matters so much. It's the reason a kilobyte isn't a nice, neat 1,000 bytes, it's 1,024 bytes. A megabyte is 1,024 kilobytes, and so on, all the way up the chain. This is the fundamental math behind every single file, photo, and piece of digital storage you've ever used. Okay, so we have our alphabet, these bits and bytes. Now we need some grammar. We need a system to arrange all those bits and bytes so they can represent numbers and let the computer actually do some math. This is where the whole idea of a number system comes into play. And look, it's just a fancy term for a set of rules for writing numbers. The most important rule to know is the base, which is simply how many unique digits you're allowed to use in that system. We as humans live in a base 10 world. Probably because we have 10 fingers. It makes sense, right? We use 10 digits, 0 through 9. And where you put a digit really matters. The number 5,319 isn't just a 5, 3, 1, and 9. It's 5,000s, 300s, 1, 10, and 9 ones. It's all based on powers of 10. Now here's the really cool part. Computers use the exact same logic. They just have a different base. Since they only have 2 digits, 0 and 1, they use base 2. So if you look at the binary number 1101, each spot represents a power of 2. The 8's place, the 4's place, the 2's place, and the 1's place. You just add up the on positions, so that's an 8 plus a 4 plus a 1, which equals 13 in our system. See? It's the same idea, just different building blocks. So great, we have a system that works perfectly for computers. There's just one problem. As you're about to see, it is an absolute nightmare for us humans to try and read. I mean, just look at this thing. It's a big old string of 1s and 0s. Can you tell me what number that is just by glancing at it? Could you spot a mistake in there? No way. It's just a wall of digits. And this is a huge problem for programmers and engineers who actually have to work with this stuff directly. This brings us to a really important question. How in the world can we make this long, ugly binary string more compact and human-friendly, but without actually changing the 1s and 0s the computer needs? Well, the solution is pretty clever. We use other base systems that are neat multiples of base 2. There's octal, or base 8, which groups binary into sets of 3. But the real king of shorthands, the one you'll see all over the place, is hexadecimal, or base 16, and that groups binary digits into perfect little sets of 4. And here is why hexadecimal is just so perfect for this job. A group of 4 bits, that's a nibble, remember, can represent 16 different values, from 0 all the way to 15. So hexadecimal gives each of those a single character, the numbers 0 through 9, and then the letters A through F for the values 10 through 15. It's brilliant. Each hex character is a perfect substitute for 4 binary digits. And this really gets to the heart of it. Hexadecimal isn't for the computer's benefit. The computer is perfectly happy with its ones and zeros. Hex is for us. It's a compact, much less error-prone way for people to read and write the machine's native language. This is the kind of stuff that makes modern software development even possible. And I guarantee you've seen this out in the wild, even if you didn't realize what it was. Anytime a web designer picks a color, they're probably using a 6-digit hex code. That code, something like #FFFF for pure white, is actually just 3 pairs of hex digits that stand for the amount of red, green, and blue light in that color. It's all just a convenient shorthand for binary. Okay, we've totally cracked numbers, but what about everything else? What about the words you're reading on this very screen? How do we possibly get from numbers to actual language? The logic here is actually beautifully simple. Think about it. If we can represent any number we want, then we can just create a giant dictionary that assigns a unique number to every single character we want to use. Every letter, every punctuation mark, every symbol. We call this amazing system character encoding. Back in the day, there was a system called ASCII, which was great for English, but pretty limited. Today, pretty much the whole world runs on Unicode. It's this massive, universal standard that assigns a unique number to characters from almost every language on Earth, past and present. And yes, that includes emojis. It's the reason you can text someone in a different language on the other side of the planet, and it just works. And that brings us full circle. From the simplest possible state of a single on-off switch, we build up to bytes. Then, using number systems, we give those bytes value. And with character encoding, we give them meaning. Every single thing you're seeing and hearing right now is just a clever, layered translation of our complex world into simple, predictable patterns of zeros and ones. When you really boil it all down, our entire digital life, every photo we take, every song we listen to, every message we send, is just an incredibly long and structured conversation happening in the language of zeros and ones. It really makes you wonder, what complex new ideas are we going to translate into this beautifully simple language next?